Hi, my name is Farid Seifi, and I'm working in the Knowledge Systems Lab in Department of Learning Health Sciences at University of Michigan. And I'm going to talk about the chatbot that we created for computable biomedical knowledge artifact retrieval and execution. With a vast and ever-growing amount of biomedical knowledge, it can be challenging to ensure that different stakeholders have quick and reliable access to this information and can effectively utilize it. So in this work, we explore new potentials for addressing these challenges by creating a chatbot that leverages retrieval-augmented generation, or RAG, with a large language model, which in this case we use ChatGPT. Developing this chatbot allowed us to examine an emerging way for healthcare professionals, researchers, and patients to find and use CBKs via typical online chat interactions. So here is how our chatbot works. Our chatbot has access to a collection of CBKs stored in a vector store. And then once a user sends a question to the chatbot will send a request to the large language model through an API, providing question, instruction, history of conversation, and the vector store. And then the large language model will process that and provide a response that may include a piece of code that comes from the CBK to the chatbot, and the chatbot will provide the final response to the user. So in the examples that we will see next, we provided precision prevention recommendations as CBKs, and here is an example of a general question that we asked the chatbot: how can you help me? And we see that it responded with, I can assist you with various health-related calculations and recommendations, and provided some examples of that. One of those examples is diabetes screening, and it says that it can calculate that if we provide age and BMI of a patient. One limitation that I should mention here before moving forward is that the large language model, when it's used with RAG, it has token limits for context files, so it can't use all of the context files to provide an answer. It needs to find the most relevant ones. And because of that, we can expect asking a question like, give me all the recommendations for a specific patient. That's not possible to calculate, and that's one of the limitations of this approach. As a follow-up example, we provided the age and BMI of a patient, and we asked about the diabetes screening, and we see that the large language model was able to calculate and find out that that patient is included for that recommendation, and it also provided more detail about that recommendation for this specific patient. A follow-up question is asked then about the version of the recommendation that's used for that response, and we see that the large language model use the data in the metadata to answer that question. So another limitation that I should mention here is that the large language models, when they are used through API, they don't have access to all the tools, so they don't have access to a code interpreter. And therefore, when the response comes back from the large language model, it may include a piece of code that needs to be executed. And the chatbot takes care of that responsibility and sends that piece of code to a code interpreter assistant for execution. And once it receives the response back, it engages the large language model again to provide that final answer to the user that doesn't have any code in it. So in conclusion, the development of our CBK-aware chatbot using RAG with large language models marks a modest but promising step forward in improving the accessibility and usability of CBKs. The chatbot has shown potential by responding to queries about CBKs accurately and facilitating the retrieval and execution of the evidence-based code carried in CBKs. However, while the initial results are encouraging, there remains challenges to fully understanding the extent to which this type of chatbot system can effectively address complex information retrieval problems. Future work will focus on evaluating the chatbot's performance and refining the approach to test how well it meets the diverse needs of healthcare professionals, researchers, and patients in real-world scenarios. So we have a few QR codes here that you can use to access our code in GitHub or Google Colab. Thank you.
Hello, my name is Sofia Ryan. I'm a senior research associate at NORC at the University of Chicago. On behalf of the ARC Clinical Decision Support Innovation Collaborative, I'm presenting our work exploring the use of artificial intelligence to scale patient-centered clinical decision support. First, I'll start with background on the ARC Clinical Decision Support Innovation Collaborative, or CDSIC. Established in 2021, the CDSIC creates a learning community to share and advance knowledge, resources, and methods for PCCDS, promote the practice and adoption of high-quality PCCDS, and advance standards-based CDS that can be shared and scaled across the U.S. healthcare ecosystem. Next, I'll provide background on PCCDS. PCCDS is a form of CDS that supports care for individual patients or specific patient populations and significantly incorporates patient-centered factors related to knowledge, such as evidence-based findings from patient-centered outcomes research, data, such as patient-generated health data or patient-reported outcomes, delivery that directly engages patients or caregivers via apps or patient portals, and use that involves patients and caregivers. Scaling refers to efforts to expand the wider use of PCCDS across health systems and patient populations. While PCCDS is promising, its adoption and scaling remains limited compared to its potential due to a variety of factors, including technical implementation challenges, costs associated with creating and maintaining PCCDS, and a lack of robust evidence for clinical, workload, financial, and efficiency outcomes of deploying and using PCCDS. These challenges limit the shareability and reusability of PCCDS across settings. As the use of AI becomes more ubiquitous in healthcare, a promising approach to address barriers to the adoption and impact of PCCDS is to leverage the increasing capabilities of AI, including large language models. However, there's not yet been an exploration of the opportunities, considerations, and recommendations for the use of AI to scale PCCDS. To address this gap, the CDSIC conducted a landscape assessment to present key opportunities and considerations for the use of AI to scale PCCDS. The landscape assessment was informed by a rapid literature review and key informant interviews, including patient representatives. The scope of AI considered in the assessment includes machine learning techniques, including large language models and generative AI, and sophisticated rule-driven approaches. Findings from the landscape assessment are organized across 5 dimensions of scaling, shown here. AI is currently being used to scale PCCDS in various ways across scaling dimensions. Most notably, AI is being used to synthesize information from a patient's record, create and improve PCCDS logic, create treatment recommendations based on patient-provided health data, and conduct data transformations across health systems to make PCCDS more shareable. Presented here is a high-level summary of the landscape assessment findings. Challenges related to using AI to scale PCCDS include the black box nature of AI and potential for bias in results. Additionally, there are challenges with workflow integration, and there's limited reporting about the development and validation of AI-based tools, which limits replication across settings. Common unintended consequences included hallucinations in AI-generated output. Promising practices for using AI to scale PCCDS centered around viewing AI as a partner to, rather than a replacement for, human interaction, promoting the use of explainable AI to build trust, additional education for clinicians and patients on how to incorporate AI-based tools into their workflows and life flows, and improve standards for reporting and external validation of tool development. Strategies to ensure patient safety and privacy focused on adhering to ethics principles, addressing biases in output, and exploring the use of synthetic data to train AI-based PCCDS. Our findings reveal several gaps that can be addressed by future research, including techniques to reduce AI hallucinations, improved integration of AI-based PCCDS into clinician workflows and patient life flows, and improved reporting processes. With continued testing and evaluation, the potential to leverage AI to scale PCCDS and make patient-centered care more efficient, safe, and accessible for patients will become clearer over time. In conclusion, the findings from our landscape assessment will enable stakeholders to better understand and leverage AI to scale PCCDS more widely. You can read the full landscape assessment by scanning the QR code on the screen. Thank you.
Hi everyone, and welcome to my presentation, Leveraging Generative AI for Automating Quality Indicator Knowledge Object Creation. I'm David Fraile Navarro. I'm a medical doctor and a PhD on applied NLP. and I'm an AI scientist at Evidentli. So before we start, this is what I will be covering in this lightning talk. What are ECQMs, why they matter, what is the challenge that we face, and how we solve this challenge, and the next steps and future plans for this technology. So ECQMs stands for Electronic Clinical Quality Measures, which basically what they do is they are used as measurements to monitor the quality of the healthcare provided. This is usually conducted annually, and it is mandatory for every provider in America, in the US, to qualify for Medicare or Medicaid reimbursement program. So they have to calculate these ECQMs, or at least a subset of these ECQMs. So these days, there is actually a whole industry surrounding the calculation on measuring these ECQMs. At the moment, it's quite expensive and it's a time-intensive task. So that's why we saw it as an opportunity. So this is how ECQMs generally look like, which is a performance rate. It's to simplify a percentage of something. And usually it has these two main components, a numerator and a denominator. So for instance, how many of all my diabetic patients, how many of them have their blood glucose measured the last month? And that will give you percentage of patients. This percentage then will allow us to infer how was the quality of the healthcare provider based on that. Of course, this is a very simplified version. Then some performance rates or some of these indicators are a bit more complex. They have inclusions and exclusions of several cohorts or sub-cohorts. They might also include temporal relations, like this needs to be measured in the next 24 hours after another event happened, and so on and so forth. So it gets more complex than this, but this is the main idea. And this is how they actually appear in the ECQM website. There is this general description of the quality indicator, the criteria, and the inclusion-exclusion criteria, and the different components. So that is our challenge, how we move from this free text information into a executable workflow that we can use in Piano, such as this one that we created before. It took us 12 weeks to do one of these indicators, and for the last year version, there is 60 indicators. So that will take us 13 years to complete. So it will then be feasible. So that's the challenge. Translate from ECQM to Evidence Hub first, which is our platform to share knowledge objects across Piano and across the community, and then import them into Piano so they can be executed as workflows. And that's how we do it. We use generative AI, and the way we use it is to extract this unstructured information from ECQM resources, including the numerator, denominator, exclusions, structure this information in several steps, then also generate with the generative AI some complex prompting OMOP compliant database queries. So we retrieve the information we need from our SQL database. And once all these elements are created, they are integrated into a Piano compatible configuration file that also can be uploaded to the Evidence Hub to be reused. So the next step for us in the future is to generate all of these ECQMs. Then we will stress test them, we will validate them thoroughly, and the idea then would be to make them available to the community in our Evidence Hub portal to be used in Piano and to be used by any researchers. So we see this also as a potential pathway to automate any sort of quality indicator in the future. So yeah, that's about it. Thank you very much, and any questions or feedbacks are welcome. Thank you.
Hello, thank you for tuning into this talk on digestible directions, the case for bite-sized standards in medical knowledge. I'm Dr. Shyam Dhokia, a clinician and software engineer at Eolas Medical. With healthcare professionals busier than ever and the volume of medical evidence ballooning year on year, delivering robust, actionable clinical guidance at the point of care is paramount. The Eolas platform serves healthcare professionals by providing real-time access to clinical guidelines, enhanced by semantic search and generative features like retrieval-augmented generation-powered question answering. Like most large language model-powered applications, a key step in our application is the chunking of text into semantically coherent pieces that form the basic unit of AI-powered knowledge models. The impact of precise semantic chunking on the quality of search results and generated content is well established. In the medical domain, a significant challenge is that Tier 1 evidence is often presented in extensive, verbose documents that are extremely difficult to chunk. Key information will use unique acronyms, be spread out across the document and therefore in different chunks, and each chunk may contain extraneous, distracting information and use inconsistent terminology. Here we show an example of two different guidelines, our structured guidelines and a more traditional guideline, and the answers that we have generated from the retrieved context. The NICE guidelines here are in a more structured and API accessible form. They are served in semantically clear bullet points for each recommendation. The guidelines from the European Association for Study of Liver is written in the prosaic style of a traditional medical research paper, like many national and international guidelines. We ask a fairly specific question, and both retrieved texts contain similar information that allows for a comprehensive answer. However, NICE has retrieved all of this information in one chunk, whereas on the EASL side, this is retrieved in 3 chunks from different parts of the document. As you can see here, the NICE answer is quite comprehensive. It has the recommendations tagged and is easy to verify. There are some issues with the answer from the European guidelines. Points 1 and 4 offer overlapping, vague advice, essentially repeating the same information. Point 2 refers to similar guidance to point 2 in the NICE answer, but it misses additional information like specific levels, as this was presented in a table elsewhere in the document and not accurately parsed. Point 3 appears to be hallucination, and a potentially dangerous one. There is no mention of liver biopsy with regards to these specific cutoff values in the quoted context. There are many additional considerations as well for more structured and machine-readable format for guidelines. There's the cost and the latency of retrieval. More chunks means more time and more compute, as well as cost and latency in generation as well, with a greater context window. There's the accuracy of the text parsing and tidying up from PDFs and HTMLs, and inaccurately parsing medical documents could be potentially quite harmful. There's the accuracy of parsing tables as well as picture data as well. With these kind of more granular guidelines, there's a potential to update specific guidelines one by one rather than an iterative update where the entire recommendations are updated. It also offers us more powerful deep linking capabilities as well, where we can direct users to references for specific information rather than the whole doc or various sections. And this, of course, provides better explainability to the user about where this answer has come from. As an overview of the impact that Eolas is already making in hospitals in the UK and beyond, Eolas is used in 80% of NHS hospitals with 100,000 active clinicians using the platform this month. Just with our fundamental semantic search features and providing these national and local guidelines, we've seen a 5 times reduction in the time spent by physicians seeking information with Eolas. With the potential of a RAG-powered application, we can go even faster and have disparate and complex information hidden within 100-page documents, easily accessible within a few seconds and presented to clinicians at the point of care in an easy to digest format. Thank you.
Hi, my name is Jinghui from the Australian eHealth Research Centre, CSIRO. We're happy to present our talk on a four-pillar framework to evaluate LLMs for diagnostic support, a joint work with Anthony. Large language models, or LLMs, have shown amazing capabilities in understanding and processing human language, and they have extracted significant interest in applying them in healthcare. Many recent studies demonstrate that LLMs can answer a wide range of medical questions with high accuracy. Just as the title of this study from Nature goes, LLMs encode clinical knowledge, which can be elicited by simply interacting with them using some natural language prompts. However, how can we ensure that LLMs indeed encode the relevant clinical knowledge we care about? Existing evaluation methodologies, LLMs' diagnostic capability, predominantly focus on question answering accuracy, which unfortunately neglects many other crucial aspects related to the stochastic nature of LLM as clinical relevance. For example, we know that LLM can flip its answers to questions rephrased in a different way or fail to make use of supporting evidence. To address this gap, we propose a four-pillar framework to evaluate LLMs for clinical diagnosis that goes beyond basic Q&A. The first pillar measures the breadth and depth of factual medical knowledge encoded by LLM, which involves performing Q&A style evaluation using curated medical questions. This is similar to most existing studies. What can be done further in this direction is to leverage ontologies to derive and synthesize high-quality questions to scale the evaluation. The second pillar aims to evaluate the accessibility of the knowledge. This is based on the observation that LLMs may respond differently to different prompting and decoding strategies. For example, recent works have shown that some proper prompt engineering can improve GPT-4's accuracy on medical Q&A by a large margin. Also, for a question that LLMs give the wrong answer, if we repeatedly sample from LLMs, there's a chance that they can finally get the correct answer. This is often appear as the best of sampling. We believe it is therefore important to evaluate the accessibility of the LLM's knowledge by quantifying the easiness to reliably elicit such knowledge given appropriate prompting and decoding methods. The third pillar assesses the capacity of LLMs to be augmented by external information sources so that LLM can adapt its knowledge to context. This mirrors clinicians who consider multiple data sources and tools for a full picture of patients when making diagnostic decisions, which contrasts with existing Q&A evaluation that considers little or no clinical context. This requires LLM to effectively access, analyze, and integrate information from EHR and results from other diagnostic tools such as genomics, pharmacy records, wearable devices, and so on. Finally, the fourth pillar evaluates LLM's capability to reason over a specific diagnosis by justifying its answer. This requires LLM to provide clear reasoning steps that lead to its answer, such as chain of thoughts. But beyond that, we believe it is important to make sure that each of such reasoning steps is verifiable, and that intervening one or more of these steps would lead to a corresponding change of LLM's final answer. Evaluating the validity of the reasoning process also encourages applying LLM to generate plausible diagnostic hypotheses that could be useful in practice. To conclude, LLM is a new approach to encode and mobilize CBK with a lot of potential and possibility. Making sure its validity and reliability is that's very important. So here we present a four-pillar framework to measure LLM's diagnostic knowledge, and we hope it can inspire the development of better evaluation benchmarks to make sure LLMs are usable and available in the clinical practice. Thank you so much for your attention.